For the second day of this 1 week faculty development program on 3D printing and design, organized by Bharatiya Vidya Bhavan, Sardar Patel College of Engineering, and sponsored by All India Council for Technical Education's Training and Learning Academy. It gives me immense pleasure to introduce you all to our today's eminent speaker for this session, Dr. Dr. Kiran Suresh Bhode sir. Dr. Kiran Bhode sir have received PhD degree in mechanical engineering from Indian Institute of Technology, Bombay, Mumbai. He is an associate professor in the Department of Mechanical Engineering at Sardar Patel College of Engineering, Andheri. His research interests are in the areas of fabrication of microstructures using bulk photopolymerization and development of flexural systems. He has authored over 30 peer-reviewed conference and 16 journal papers. Further, he has also research projects sponsored by Science and Engineering Research Board, SERB, DST, Technical Education Quality Improvement Program 2, TechWhip 2, and Indian Nanotechnology Users Program, INUP. I further request Dr. Kiran Suresh Bhore sir to kindly start the session.
Thank you, Sadhvi, for the generous introduction. I welcome all the participants and good morning all. Good morning to all the participants. Let me share my PPT with you. Just quick feedback. Are you able to see the? Are you ab- are you able to see the? Yeah. Okay. Yeah. So there is echo coming. Okay. Yeah. So you are able to see my PPT, right? Yeah. Okay. Good.
Yes, sir.
In this particular talk, I will be discussing about the two processes, and these are the outcomes of the two PhDs, or I can say these are the PhD stories of two PhD stories, which has developed these two processes. First process is a micro stereolithography. In short, I may call it as MSL. So MSL is a micro stereolithography, and another is a bulk lithography. Both of these processes I will be discussing with you in this particular talk of 2 hours. Now, for what purpose these two processes are? So both of these processes are for the 3D microfabrication. So this FDP is focusing on the additive manufacturing. These two processes are dealing with the additive manufacturing processes, but for the micro printing, not for a meso or macro size of printing, but they are related with the microfabrication or the micro printing. So these two processes are emerged from the MEMS. I mean, these are the MEMS processes. MEMS means micro electromechanical systems. And where do we use the MEMS? So this slide depicts all that. So we have a lot of application of the MEMS all around us. We use the phone, I mean mobile phone. There are plenty of sensors available in mobile phones, gyroscope, accelerometer. We often play, or the kids play, the games using the mobile. And there are a lot of tilt action, acceleration action that happens to an object, and that is because of the acceleration or gyroscope which is having in the mobile phone. So all that they are the micro devices or the micro electromechanical systems. We have plenty of such sensors which are used in the automobiles, and few of the sensors used in the automobiles are mentioned here. We have manifold air pressure sensor, we have the mass airflow sensors, we have the airbags. Okay, for the deployment of the airbags, we have the tire sensor, we have exhaust gas sensor, we have crash sensor, fuel sensor, then microphones for the noise cancellation, and fuel pressure sensor, and so many sensors. If you take the high end automobile, we will find almost 1,000 order of the like sensors which are having in the car or automobile of class of Mercedes, and not like not very less in case of the ordinary cars as well. I mean, as per the recent norms, these airbags and all these are common features. So there are so many sensors which are used in the automobile as well. We have plenty of application of the micro electromechanical systems in medical area as well. We will see this in the next slide. And also we have plenty of sensors that are used in the industrial application for the automation, etc. So in all these sensors, these are the micro devices and developed using some of the processes. And one of the processes is nothing but the micro 3D lithography for 3D micro printing or the bulk lithography, which I am going to talk. So in the MEMS in biomedical application also have plenty of like the area in which they are working. We have joint angle stimulator, then bladder stimulator, a lot of prostheses, then the blood pressure sensor for pacemaker and all. These are few of the examples where the micro electromechanical system works. And if we have to fabricate the 3D components or the 3D structures in micro electromechanical systems, promising technologies are nothing but the micro 3D lithography or the bulk lithography or the LIGA. The two processes which I am going to talk are the micro 3D lithography and another is the bulk lithography. Micro 3D lithography, in short, I will be calling as MSL, or generally it is called in short as MSL system. So this I will be explaining or discussing first with you, and then later on I will be discussing with you the bulk lithography, which has emerged from the micro 3D lithography. In fact, before starting this particular discussion on the micro 3D lithography, this process is developed. The process which I am talking about, the micro 3D lithography, the kind of the variant of the MSL which I am discussing here, is the outcome of the PhD work of one of our participants of this MDP, Dr. Suhas Deshmukh. So it is his work, his PhD work. He was senior to me in my lab in the laboratory, Suman Musrola Advanced Microengineering Laboratory of IIT Bombay. And the majority of the work which I am presenting here is of his contribution towards PhD. And later on, I worked and I improvised this process that is the bulk lithography. So later on, I will be discussing that particular part. So let us discuss the micro 3D lithography first. So micro 3D lithography is a 3D additive manufacturing process for the micro printing. So 3D micro printing, it is basically a 3D micro printer. So micro printer means what? Like what ranges of the size you are looking at when we are calling at micro printer? So the micro printing means I am looking at the sizes which is ranging from 1 micron to 1000 micron. So this is the size range, 1 micron to 1000 micron. Imagine such a small size. I mean, to give the feel of some these sizes, our human hair is of the diameter of 80 to 100 micron. So human hair is of diameter of 80 to 100 microns. So you can imagine how small the object is to be printed. The 3D object is to be printed. So in this particular MSL, the systems we are developing, micron systems we are developing means we may be developing a gearing system or a turbine system in such a sizes. I mean 1 micron to 1000 micron. Imagine, okay, gearing system you have to develop or the turbine system you have to develop in such a small sizes. So there are a lot of challenges that comes when we are going to develop the 3D micro printer. What it starts with, the general process of this the MSL is common to all the additive manufacturing processes. So we first of all what we do is the thing, but we develop a CAD model. So we develop a CAD model in any CAD modeling software. So still we are in a computer, the object is not realized in actual. So the computer model the model is developed in a computer, and that CAD model can be developed in any software such as the Pro-E or CATIA, SolidWorks or Autodesk or something like that. So you can use this any of this CAD modeling software and you can develop a CAD model. So this is the first step. And then what we do in additive manufacturing mostly is what we are doing is we are slicing it. So this 3D CAD model is sliced into the number of 2D planes. Okay. So this particular slice planes are these are used to slice this particular 3D object. Okay. So after slicing, what we are going to get is nothing but the number of 2D planes. So the 3D CAD model is sliced into the number of planes and we get the output as the 2D planes. So this is the example taken of the cone type of a structure. So when we slice it, we are getting number of circles out of it. So these particular circles are the outcome of the slicing program. Again, we can develop our own slicing program or there are many open source softwares also available which slice the 3D CAD model and it gives you the number of 2D planes. Next, what happens? These 2D planes are fabricated one by one in the setup. So setup consists of this for this MSL I'm talking about specifically. The setup consists of the arginine laser and this arginine laser is then passed through a switch that is the optical switch and then the laser light is falling onto the mirrors and through the mirrors from the mirror the laser light is guided onto the photopolymer vat through a focusing lens. So the light is focused exactly here, okay, on the free surface of the photopolymer. So there is a photopolymer and wherever the light falls this liquid photopolymer turns into the solid, okay, because of the cross-linking or the photopolymerization that happens. So the light is getting absorbed into this photopolymer and the cross-linking happens and thus this liquid turns into the solid. Okay, now when we have to fabricate this particular circle over here, the first circle, very first, this platform is very much near to the free surface. So this is kept very much near to the free surface. And when it is kept very much near to the free surface, the laser is scanned and when laser is scanned through this mirror which is acting on which is actuated onto or placed onto the scanner, when this particular the laser light is scanned, we can see whenever the laser light is outside the circle we don't want there the curing to take place, means polymerization we don't want there. So the laser need to be off there and it should be on for this particular only specific specified small portion which is within the circle here. So laser should be on within that circle only and again off. If you take the second line scan, the laser should be off from this point to this point and then again laser should be on from this point to this point. So the laser should be on within the circle and off outside the circle while scanning. So after the slicing of this particular the CAD model, we are getting the 2D plane. But after that 2D plane, when we have to fabricate this 2D plane by layer scanning or line by line scanning the laser light onto the photopolymer solution here, we required accurate scan path program. So this scan path program will scan the laser path and this laser path scan path program will be giving us the output such as the xy position of the laser and also the laser on off data. Okay, so these are the two very important. These are the two a very important data which the scan path gives laser on off data and also the laser position data with respect to xy with respect to the time t. So this particular data is given to a microcontroller to the scanner and the optical switch. So optical switch is to make the laser on and off at the desired point and the xy position with respect to the time is given to this xy scanner. When it synchronized, then we get in the scan path, and thus we get this first layer getting developed. This first layer is getting developed, which is very near to the free surface initially. Once the first layer is developed, then we dip this particular platform inside the photopolymer resin, and a fresh liquid comes on the top of the previously formed layer. Okay, so fresh liquid comes. And when fresh liquid comes for the second layer, whatever the second layer we have sliced, the scan part data is obtained for the second layer, and the second layer is also given to a microcontroller. So second layer also is fabricated. This second layer stick or bonded with the previously formed layer. Okay, and thus we go on doing this addition of the layer and the entire 3D component, this entire 3D component can be obtained. So this is the process step for the fabrication of the 3D component layer by layer way in the this MSL process. Okay, very important as I said, this is for microprinting. So we are going to develop these systems or the structures which are in micron size, and the micron size I have given you that the ranges is 1 micron to the 1000 micron. Okay, such a small sizes of the features we are doing at or we are developing at. Maybe a gearing system, you may have to design a gear within some 500 micron, maybe for example. So what are the challenge if we are taking a scanner here? This particular scanner, the when it is scanning this laser line, and if you're using a straight line scanner, which is based on the conventional straight line mechanism that you might have, particularly the mechanical engineering background participants might be aware of the straight line mechanism. So conventional straight line mechanism, if we are using it for scanning this particular laser data, laser path in such a way, then and if we are fabricating a component of such as 500 micron and so, what is going to happen? Let us throw a light on that. So the conventional mechanism consists of the rigid bodies. So it consists of the two rigid bodies. One is this body and another is this particular body. So two rigid linkages and which are connected by a pin joint. So here is a pin joint. So these two bodies, if this is rotating, then this also where motion will be transmitted to this another rigid body here. Okay, and that particular movement will be transferred through this particular joint, that is the pin joint. So this is the pin joint. Okay, over here. Now the pin joint, if that itself that pin joint will have a clearance, and that clearance will be in micron size. Okay, so the if the pin joint is having the clearance in micron size, what will happen? Ideally, when we are scanning the laser light in this, and if this, I mean, coming back to this particular configuration here, two rigid bodies connected together by a pin joint, and pin joint is having a clearance in micron. Let us say 500 micron is the clearance. So what will happen when we are scanning the laser here, rather than following this particular straight line path, it may follow this path. So rather than going in a very straight line like this, it will follow like this particular line, and this line it will follow because the clearance itself is in 500 micron. Understand? Okay, so this will happen. So what is the point to tell that the conventional straight line mechanism will not solve the purpose of like fabrication of this particular 3D structures. Okay, says conventional straight line mechanism is going to have the clearance in micron and error, that's why it will be in micron, and this is the problem that will happen. Ideal line to be traced is this, but actual line traced will be like this, and you will lost all over the accuracy, and this fabrication will not be possible. Okay, so what we required is a very accurate the XY scanner which can give the accuracy in nanometers. Then only it will be possible to fabricate the component of the micron size, right? So this is one very important challenge that is having. Number one is the you should have a good scanning mechanism, and the conventional mechanism or conventional straight line mechanism will not be the very good choice for this kind of a systems. Another very important point is that when we are developing this 3D structure over here through layer by layer addition, for smooth fabrication, we need to slice this component in number of planes. If we have the more number of planes sliced, more number of slices, then the lateral surface will be of good finish. I mean, lateral surface will have a good finish. If we have the coarse, uh, uh, I mean, slicing, then we will have the stair stepping effect. I mean, this is the typically, the first layer, if it is a form like this, and second layer, if it is a coarse structure, then form like this, sorry, form like this, third will be like this, and so and so. So if you can see, this is the stair stepping effect that is generally being observed, and that is not good. So to avoid this staircasing effect, we need to slice the component in large number of planes, but large number of planes slicing will lead to large fabrication time. Okay, another important, if you are allowing large number of slicing plane, and you are going to give the time for the fabrication, that is not an issue. But still there will be a problem that this particular resin surface is having some kind of a viscosity, and that will not flow readily for the minimum thickness which you are designed. Let us say if you slice, and the distance between the two slices is 5 micron. So the layer thickness what you are intended to do in the fabrication is of 5 microns. But that, are you going to get that 5 micron, the layer thickness? It is very important point, because in actual fabrication, what will happen if this resin, this photopolymer is of the having viscosity in order of something like the honey, or maybe a clay or grease type of like resin, or honey type of, for example, if you take that is easy to understand, then if you dip this particular platform, are you going to get a 5 micron fine layer on the top of this platform? Very important point. It is very it is very impossible to get such a low or such a lesser thickness of the layer on the top of the platform, because when the viscosity is high, it will build onto the edges. When we are dipping this particular platform, let us say this is the platform, and we are dipping into the resin, then what will happen? Resin will flow over the edges, and but it will not flow over this particular plane. Okay, and only when the threshold thickness is achieved, that threshold thickness may be few of the in consist when we are taking a resin of some honey type of a structure, and when it will have some type of some thickness in terms of the then only it will start probing and the layer will be formed. So that is a practical difficulty. You cannot maintain layer of a minimum thickness whatever desire. You can slice it in a computer of for whatever the slice thickness, but in practical it is not possible. Okay, it depends upon the viscosity, surface tension, these properties. So we have so many, I mean, different variants for this, and so many different techniques for the minimum layer thickness to achieve. So that is beyond the scope of this particular talk. We can, like, someone interested can discuss with me later on. So these are some of the challenges that we are having when we are 3D printing the micro components. Okay. Then further, very important, the laser which we are using here in the process of MSL is generally the argon ion laser. Mostly the argon ion laser is used. Some people have tried the NDI laser as well. But in the laboratory where we work, we have used the argon ion laser, and that argon ion laser is having the wavelength of 351 nanometer, and that laser is having the Gaussian intensity profile. You can see here, this is a Gaussian intensity profile, and when we are focusing this laser light onto the photopolymer resin over here, what happens only when the energy of the laser is beyond critical energy of the resin, beyond critical energy of the photopolymer resin, then only the photopolymer get cured, otherwise it will not get cured. So it is essential that the energy of the laser system needs to be beyond critical energy of the resin. So if we take this intensity profile, and this is the profile beyond which the energy is beyond critical energy of the resin, then only the photopolymerization is going to take place, right? And as a result of that, and the Gaussian profile we are having of our the laser. As a result of that, we will say when the laser is scanning, we are not getting a rectangular plane or rectangular line of a rectangular cross section. Rather than that, we are getting a cross section of the Gaussian in nature. So this is a CD, which is a pure depth, and this is a line width, and this is the line which is getting traced by the laser beam. Sometimes it happens that if the component is vertical in nature, we can have the coarse slicing. I mean, the slicing to have the faster production, we can have the coarse slicing because the vertical wall is the lateral surface is vertical. Then we can go for a coarse slicing. But the coarse slicing again cannot be of any distance. This is the limitation. The line which it is all. I mean, the getting cured is not of a rectangular cross section, but it is of a Gaussian cross section. So this puts the limit on the maximum layer thickness as well. So these are some of the points which are to be remembered or which are to be kept in mind while designing the process plan for the fabrication of the component using the MSL. Now, what are the different types of the MSL? So what I have mentioned to you or discussed here is the scanning type of the MSL where the focus point is scanned line by line scanning, the layer is formed, and then layer is formed onto the platform that is dipped, and second layer is formed by line scanning, and so and so. So this is called as the free surface technique. So it is a vector by vector micro 3D recovery process where it is this is scan laser light is scan on a free surface technique. You have another technique called as a constant surface technique. So what is done in a constant surface technique is you have the here, otherwise I will explain here. So you have the one transparent substrate placed on the top of the resin. So on the top of the resin you have the transparent substrate here, and this is the build platform, and the laser light is focused exactly below the transparent substrate, and very thin layer is maintained between this transparent substrate and the build platform. Okay, and what I told you, when we are going to dip this particular platform, when the viscosity of the resin is very high, it is not going to flow very easily onto the platform. Okay, that type of the problem is not seen in case of a constant surface MSM, as the platform is within the surface and it is dipping within the surface. So this particular building the resin onto the top of the surface of the build platform, that effect will not happen or will not take place, and thus the constant surface is going to have the high resolution compared to the free surface technique. But the very important problem is that when we are having the resin in between these two surface and we are curing that, it may likely happen that the cured structure also will stick to the top surface, and ideally the cured surface should not stick to the top surface, right? It should be free from detachment. I mean, it should detach the top surface and it should be attached with the bottom surface. And with respect to the time, that property of the detachment will not be existing, and thus it will put on some limitation in the actual limitation in the employment of the constant surface. But still, we in our laboratory, Mr. Dada Saheb Rupnawar, one of the PhD scholar, has tried this constant surface and he has obtained the layer thickness as low as 5 micron, and that is nobody has achieved so far this resolution. So 5 micron layer thickness he has attained with the constant surface technique. So this is about the vector by vector scanning micro 3D lithography. What about the another variant I'm talking about is nothing but the projection MSL, projection micro 3D lithography. So what we can do in projection micro 3D lithography is, rather than line by line scanning this laser onto the photopolymer and curing this 2D structure, we can project entire this 2D surface by projecting it onto the photopolymer. So similar to the projector which we are using while teaching, the same kind of a projector we can use, maybe a DMD or LCD type, but I mean principally it is same. The projection is used, and that entire the 2D layer is projected. Entire 2D layer is projected onto the resin surface. And in one projection or in one exposure, the entire 2D surface get cured. So that is called as the projection micro stereolithography. So you have the two variants there. One is liquid crystal display. I mean this is the variant based on the projection which we are using. So one is a liquid crystal display and another is a digital micromirror device or DMD. So it is obvious that when we are projecting entire 2D surface in one go, the entire 2D surface get fabricated in one go, like rather than line by line scanning and developing the 2D surface. So this kind of the projection micro stereolithography is very much faster than that of the line by line scanning the projection of line by line scanning the scanning of the micro line by line scanning micro stereolithography process. So this is much high in production rate, but this leads to the resolution. I mean, is not at par with the line by line scanning, because in line by line scanning we can do scan. I mean, we are focusing the laser light, and the focus spot is very small size in compared to the projection type, and that's why it is very much faster. Okay, and we can print the minimum feature size very easily in case of the line by line scanning or focus spot scanning, rather than the project entire projecting entire the 2D image. Another very important thing which I would like to tell you before moving to the next slide is that uh, when we are doing vector by vector scanning of the focus light, so this is the mirror which we are having, and for a scanning, we generally people what generally have used is the tilting this mirror, and by tilting the mirror, this particular scanning is done. So this is the focus spot coming here, and this focus spot is scanned over the line in this, let us say, in this direction, by tilting this mirror. So these mirrors are tilted, and when they are tilted, this particular focus light is getting scanned in a particular direction. Okay, so this is what happens. So obviously, what happens when we are tilting the mirror? By tilting the mirror, the focus spot do not remain constant all over the free resin surface, right? So all over the free resin surface, the this particular focus spot do not remain constant. And based on this tilting the mirror, there are so many strategies which are there, and these strategies are post objective, pre objective scanning, and so and so. So the pre in post objective galvanometer scanning, we have the scanning by the mirror rotation. So we have the mirrors rotate, and this particular mirror, when they are rotate like this, M1 and M2, these are the two mirrors which is we are rotating. Then we get the scanning of the laser light in the X and Y direction. And in this post objective scanning, we have the lens first and the mirror later. And it is obvious that when we are having this scanning done by the scanning done by rotating the mirror, the focus point do not remain constant on the free surface of the resin, and thus we are going to get defocus spot all over the point except the one unique point. Right, so that is the point, and that is the point to be considered. And very importantly is that when we are having the defocus point at the other location, the energy distribution is not same energy, because it is defocused all over at other points, and so the energy will not remain same. So critical energy sometimes may not be reached, and your component may not get formed. I mean, as I said, that for curing you need to have the energy beyond critical energy of the resin, then only curing will take place. So this is very important aspect. And another is the resolution. So when it is defocus, although if the energy is good enough to cure, then as it is a defocus, spot size will be a much bigger, and that is again a very point of a concern. Second scanning is a pre-objective. In pre-objective, we have the laser beam coming from the laser source, falling onto the mirror and then onto the focusing lens. Again, for scanning of the laser, we are tilting the mirrors M1 and M2. When we are tilting the mirrors M1 and M2, again we are getting the beam scan in X and Y direction. Okay, again, it is logical that the focus point will not remain a constant on the free surface of the resin. And as it is a not constant under the free surface of the region, focus spot is only uniquely present at one of the point only, and at all other points it is a defocus point. Because of this, again, there is a resolution problem and there is a curing problem that may happen. So I acknowledge this for the Dr. Suhas Deshmukh and Prasanna Gandhi for this. This is published in JMPT Journal in 2008. For those who are interested to look more in detail, can look in that particular paper. Third scanning scheme is off-axis lens scanning scheme. So off-axis lens scanning scheme. So we are having a laser here. So rather than the mirrors, what we are doing is that this particular lens we are moving. The lens is moved in x and y direction, and when the lens is moved in x and y direction, again, what is the problem is the intensity profile is distorted due to the off-axis motion. The intensity profile will not be remaining constant. The intensity profile will be perfect when the laser beam is centrally at the lens and then focus onto the free liquid surface. And to avoid all these problems of the intensity profile getting distorted or the focus point is getting distorted all over the scan, then the next scanning scheme has been developed by the Professor Ikuta, and that is by from the South Korea. I think he is from that group has developed this scanning, new scanning called photoreactor tank scanning. So here the you are in photoreactor tank scanning. So this is the tank. Tank is moved in photoreactor tank scanning. So tank is moved in x and y direction. And yours this mirror which is on the scanner. So scanner is not there. So this is a mirror which is fixed. Okay, focusing lens is fixed and tank is moved. So when tank is moved, you can see here this is a focus spot, and focus spot do remain constant all over, right? So now there is a no problem of defocusing here, rather than the previous cases of scanning when the mirrors were tilted. So the focus spot was like this is the locus of focus spot. But now in case of the tank moving and entirely this optical system is constant, you get the focus spot constant all over the resin surface. Okay, so this is what is happening in case of the photoreactor tank scanning. Your focus point do remain a constant, and that's why this is advantageous from one point of view. But another disadvantage of this is that it cannot be used for whatever the speed you want, because when we are scanning the tank is having the liquid resin, and there will be waves that will be formed if you are scanning it or scanning this photoreactor tank at the higher velocity. And if the viscosity is low, these waves will be very higher in nature, and thus it may create the wavy structure due to the motion of the resin. So that's why this is also one of the disadvantage and cannot be practically feasible, this particular scanning scheme. Now, as we discuss all these scanning schemes which are there already in existence, right, for the MSL system, and if we do the analysis, this is analysis again done by the Dr. Suhas, and this particular the analysis told you, I mean, it gives you the idea that how the peak intensity at the 00 point, the focus was rightly onto the surface of the free liquid resin here, and when it is
Hello,
moved,
sir.
yeah,
Sorry to disturb you. Sir, can you present your screen again?
what happened? Screen is not visible.
Yes, it is not visible.
Okay,
And also increase the pointer size, sir. Laser pointer size.
okay, is this screen visible again now?
No, sir, it's not visible.
Screen is not visible.
Sir, screen is actually visible. Now it is not visible.
Yeah, I have taken out. Let me share again. Resume presenting.
Yeah, now it is in transition mode, sir. Now it is visible.
Okay, okay. Is it full screen visible now?
Yes, sir. Yes.
Yes, sir.
Yeah, okay. Thank you very much. So the various scanning schemes that we have discussed, you lost it, or you were? Shall I go back and again explain all that?
No, sir. It is a matter of seconds, sir.
Okay, okay, fine. Okay, thank you for the feedback. So we have discussed the various scanning schemes of axis, on axis, and all. With all that, we have come to a conclusion that the focus part do not remain constant on the free liquid surface, right? And the focus spot diminishes at the other point, and that was a logical, and that is simulated in the software. And we can see here that the for off axis or post objective and pre objective in all this scanning scheme, when the it is scanned at a distance of 1 to 1.5, the intensity diminishes very fast. And as intensity diminishes very fast, the energy exposure is very may not be proper, and the focus spot is also very big. And because of all that, the the we may not get the structure, which we may not get the structure of whatever the resolution that we want in the 3D printing. Okay, so this is one from the simulation which we have realized. So this is the state of art, like the what is the remedial. So this is the state of art optomechanical scanning scheme which the Dr. Suhas has this this concept has presented in his MSL process. And let me take you to this particular state of art optomechanical scanning scheme. So what happens in this? So we are having the laser source here. Laser is coming from the laser source falling onto the M2 mirror and then the M1 mirror, and this is the focusing lens, and this is the resin surface. Okay, so what we have discussed so far is we have tilted the mirror M1 and M2, and by tilting the M1 and M2, we have got the X and Y scanning, right? So what is done in the this state of art on axis optomechanical scanning scheme is the for the y-axis scanning, this M1 and focusing lens is moved together. So when M1 and focusing lens is moved together, this particular focus spot do remain constant in the y direction, right? So this is not tilted, rather than it is moved along with the focusing lens. Okay. Then the for the y for the x-axis, let us see. So for the x-axis, the M1, M2, and focusing lens all together moved, right? So when it is moved on the axis, on this particular axis, then again in the x-axis also the focus spot will remain constant. So this is the state of art on axis optomechanical scanning scheme, and this is going to give the uniform spot characteristics all around the range of the scan. And thus it is a spot size remain constant, uniformity in intensity profile, so we will be able to generate a component of large length of high resolution. I mean, you can print like the lines of like whatever the but resolution of maybe a 6 micron or 7 micron or something like that, depending upon the focus spot dimension that we are having. Further, here the resin tank is not moved at all. We are moving the optical system here, and that's why the resin tank, as it is kept constant, there is no problem. There is no problem of like wavy structure that generally happens in case of photoreactor tank scanning scheme. Okay, so this is the advantage of the on-axis scanning scheme, and again, this on-axis scanning scheme is analyzed through the software, and it is compared with all other scanning schemes such as on axis, such as off pre-objective, post-objective, and off-axis scanning scheme. So you can see in all other schemes where the mirror is tilted, and thus the scan is developed or scanning is done by rotating the mirror. There we can see the focus spot is very big at a distance other than the 0 0. Okay, at the distance other than the 0 0, even at the 2 mm distance, the focus spot means the spot size is very big. The spot size is very big, but in case of the on-axis scanning scheme, the spot size is almost a constant, and the intensity also the almost constant in case of the on-axis scanning scheme. But in all other cases, such as the pre-objective, post-objective scanning scheme, the intensity diminishes and almost is equal to 0. at a distance equal to 2 on either side. So this is very important that the on-axis scanning scheme, the concept of on-axis scanning scheme can be utilized in the fabrication of the 3D printing, 3D micro printing especially, right? And that can be used for can be employed and used. Now that concept is employed then, and then the experimental result and the simulation result are compared. You can see they are well in the agreement. This particular the for the peak intensity and also for the spot size point of view. Now, how to develop this on-axis scanning scheme? Now, concept is very important. Concept is what we have discussed, but how to develop uh, this particular scanning scheme. So it consists of the four linkages. Again, I told you initially that the in case of the using of the conventional straight line mechanism, we are having the two rigid bodies and connected with the pin joint. Pin joint is having the clearance itself in micron, and that's why they cannot be used. So what is generally is used in what kind of mechanism is preferred here is the compliant mechanism or the flexural mechanism. So we are using the flexural mechanism here in case of the in case of a straight line scanning of the laser beam. So what are this? What is this this flexural mechanism consist of? So these are four linkages. These are the four linkages B1, B2, B3, B4, and all these four linkages are connected rigidly to a rigid body here, acrylic body, which is on other on the right hand side, and all these four linkages are connected firmly fixed. The outer flexural linkages. I mean B1 and B4 are fixed to the point S1 and S2. So outer linkages are fixed at S1 and S2, and all these four linkages are rigidly connected to the rigid body over here. And the inner linkages are connected to a body on which we are having this scanning system, optical system, on which the force will be given and that will be getting displaced. So now the point to remember here is that B1, B2, B3, B4, all these are the flexible linkages. These are flexural linkages, right? They they are not they are free to bend when the applied force is acting on it. And this kind of like the system is first of all developed by the Shaurya Avatar at MIT USA, and then this kind of the configuration for straight line was used in the CD-ROM, and in CD-ROM we are having the laser light which get over to the CD which we are putting CD or DVD in our system. So that the laser light on the CD is moving, and that laser thing. I mean that lens is kept onto this particular picture link, and this concept from the CD-ROM is taken and then implemented in the on-axis scanning scheme for this micro stereography system. Okay, so what happens? Just look at like from the fundamentals point of view. From when we are having a flexural link and and a body connected at the free end over here, and another is in end is fixed. When we apply the force, then in the flexural link will bend, and we get the parasitic motion over here. Okay, parasitic error over here. So this is not moving in exactly in a straight line. I mean, this center will not follow exactly the path of the force which is exerted on this particular body. There will be some kind of the parasitic error, that is epsilon. Now, when we are having the two flexural linkages and a force coming onto this particular body over here, the flexural linkages will bend, and this is the new, uh, the state of this particular body over here, and still we will get some kind of a parasitic error here. Number three case is the four linkages which I have mentioned to you in the previous slide. So four linkages are used, and these four linkages are firmly fixed to a rigid body, but it is free to move. Okay, so this is a rigid body, but it is free to move, and all these four linkages are connected. Outer linkages among these four linkages, outer linkages are connected firmly at the point A over here, and inner linkages are connected to a body on which the actuating force is applied. So when now in this configuration, when the force is applied, the linkages move in such a way that the movement of this body is exactly in the direction of the applied force. So there is a zero parasitic error, and this is purely because of the bending of these flexible linkages. Okay, this is in situ. This happens, and that's why this particular concept is very promising and can be used for accurate straight line scanning of the laser beam, and thus it is used in the this particular the micro stereography process. This is actual photograph of the linkages that the mechanism which is used in the MSL. So we are having these four linkages. So these four linkages are of copper beryllium material. Copper beryllium material is used here, and this all these four linkages are firmly fixed to the acrylic body here, or rigid body. So this is firmly fixed to this rigid body here. And outer linkages you can see here, these are the outer linkages which are firmly fixed at this particular point, or the structure of this assembly over here. And this inside linkages are having this the body on which the force is generated from the voice coil actuator. Again, we have used here the voice coil actuator so that the there won't be any deviation in the line of the action of the force coming out from the actuator. If you use some other actuator such as the stepper motor or some servo motor and something like that, then there will be a friction involved with the components, and that may affect the direction of the force. And to avoid that, the voice coil actuators are used here, and you can see that this inner body is connected to this actuator. The force comes onto this body and thus it moves. Now this is for one direction. For another direction, again we have the four linkages: one, two, three, four. All these four linkages connected rigidly to the acrylic body over here. Inner linkages connected to this optical system on which the mirror is placed, and this body again is actuated with the help of the force coming out from the voice coil actuator. Okay, so these are the M1 and M2 mirror, which I explained in most of my schematics here. This is developed by Dr. Suhas Deshmukh in his doctoral work. And this is the arrangement of optics. So we have the argonine system and then the optical switch, the three beams we get, and out of this the first order beam is passed through it, and there are two more optics coming into the picture over here, M3 and M4, other than the M1 and M2. So this M3 and M4 are just for the adjustment purpose. If in manufacturing, if some error comes, then for the cancelling that particular error, this M3 and M4 mirrors are used. So this M3 and M4 mirror directed to the M2 and M1 mirror. M2 and M1 mirror are arranged on the scanner. Okay, the state of art on-axis scanning system, and then the laser light is passed through this mirror onto the focusing lens, and through the focusing lens it falls onto the photopolymer resin. So this is the arrangement of the optics for on-axis MSL system. This is the schematic of the design scanning MSL system. So the CAD, we have the computing system, computer CAD data, in which we develop the CAD model, which is to be fabricated, and then we slice it. So once we slice it, we get the number of 2D slices, and we run a scan path program onto the each of the slices. We get the data of the XY and XY at particular time, and also the laser on off data. This data is given to the microcontroller, and through the microcontroller given to the hardware. So the X and Y against the time, this data is given to the optomechatronic system, and the laser on off versus time, this data is given to the acoustic optical modulator. This works in synchronization way, and thus we focus the laser light, and by layer, line by line scanning, we generate the 2D plane, and from the 2D plane we generate the entire 3D 3D object. And after the formation of the each layer, the platform is dipped into the photopolymer resin, and the fresh liquid comes, and the next layer is for the laser is scanned for the next layer, and so the entire so and so way the entire the 3D object is then the developed. This is the photograph of the developed MSL system. So this is the laser argon and laser we are having. So this is the source of the laser light. Argon and laser used here is of 351 0.1 nanometer wavelength, and we can use many other the laser source as well, like NDIAG, as I told already. And if you are using the different layer, then you have to see the compatible resin. The resin should be able to absorb the photon at that particular wavelength. So depending upon your resin system, your laser system can be used, or based on your laser system, your resin can be accordingly. Then we have these acoustic optical modulator. So this is the unit. This is the optical switch. And do remember, when we are fabricating a component of size in micron, and we are scanning it very high speed, then we require the switching on and off very to some to in microseconds, or maybe a lesser than that. Then only it is possible. In mechanical switches cannot be used as as the switches for this particular purpose. The kind of the acoustic optical modulator which is used here in this process is having capability to make the system or laser on and off in a femtoseconds duration. Femtoseconds mean 1 divided by 10 to the power 15 seconds. Imagine such a small, amount of time. In such a small amount of time, it is able to make the laser on and off, like 1 divided by 10 to the power 15 seconds. Imagine such a big accuracy it is having. So these are all the challenges that typically microprinting is having, and thus it requires all these sophisticated accessories for that. Then after the optical switch, we are having the mirrors M3 and M1, M3 and M4, and then the laser light is passed through the spin hole onto the M2 and M1 mirror over here, and then we are having this scanning mechanism which already I told in my previous slides, and then the component get developed here below. So this is the development of CAD compatibility platform. This is developed in-house at IIT Bombay. The entire program was developed in MATLAB by the MTech student Amit Pathak and Alam Baraki during their MTech work, and they have used it. And then this is the CAD interface or the CAD outcome of that particular scan path and line program. This is the schematic of the system integration. So we have used, here the DSpace 1104 DS1104 platform as a microcontroller, and then we under the microcontroller, from the microcontroller, the CLP board, various units are connected to it. Like these are the DAC channels, and to the DAC channels, the RF driver, or the amplifier for the XY motion are connected, and then we are having the optical encoder mounted onto the flexible mechanism, and through them the data is collected by the microcontroller, and then PID controller is used to act upon for the accurate motion of the accurate straight line motion of the scanning mechanism. This is the electronics, all the driving and feedback system we are having. So these are the power supplies. This is the RF driver for the acoustic optical modulator. These are the RGF interpolator from the encoder. These are the current amplifier used for the voice coil actuators. The bottom one is the DSpace CLP board. We are having this DAC, all that channel encoder channels over here, and so and so. So after all this, then the scanning mechanism is developed, and then we have some these four videos which demonstrate that we can we can have the accurate XY motion and XY motion in large range, high range motion accurately for scanning the laser beam. So let us look at these videos. So this is low speed in the Y-axis scanning. I think this video is not getting played. Yeah, this is okay. Are you able to see the video? So this is high speed y-axis scanning. Is the video visible for all of you?
Yes, sir.
Yes, sir.
Yeah. Okay. So this is the voice coil actuator. You can see this is a mirror which is moving, and this bluish color is a laser light. And then this is for high speed XY scanning. So it is moving both in X and Y direction. So this is the voice coil actuator is moving this body over here. So this is another Y for Y axis, and you can see like both these mirrors are moving without, because they are mounted onto the scanner. This is a flexural based scanning system, and this is the on axis. You can see like it is moving on axis. That's why the focus part will remain constant onto the photopolymer resin. So this is high speed. So speed is high and large range. So range is also high. So as I told that with this scaling scheme, we can fabricate the large range, high resolution structure. Means we can print in but resolution is in micron. That particular component also is capable to produce, and even at a high speed. Okay, so this is all about the demonstration. Now, this is the results obtained at high speed and high precision scanning. You can see here, this is the scan path, and this blue one is a reference line, and the green one is the actual line. And we hardly can see any difference between the reference line and the actual line, and thus we can say it is very accurate. The error which is going to happen maximum at the corner, so when the state the mechanism moves 90-degree, then the error is going to happen maximum at that particular the point when the motion direction of the motion is changed. So this particular the corner is then highlighted. I mean, it is a projected in inset, and you can see here this is minus 800 and this is minus 800.5. So this is in micron. So this is zero point 0.5 micron, means 500 nanometer. And there you can see like hardly the 1/10 of this particular spacing is the error is seen here. So this is a 500 micron. So the error is in something. This is 500 nanometer. Sorry, this is 500 nanometer. Zero point 0.5 micron is 500 nanometer. So this is something in the 50 nanometer. So the maximum error in scanning is almost in some nanometer range. You can see this is another point where the this projection or the inset is taken. It is highlighted over here, and you can see this is a 0.25 and this is zero point 0.5 micron, means the 0.25 micron means almost this distance is 250 nanometer, and you can see the error is within the few part of that 250 nanometer, something around the 50 nanometer. Again, you can see this X position versus the time scanning chart, and again at the corner, this is projected over here in and presented in the inset, and you can see the error is in again in some kind of like the fractions of the nanometer. Okay, here also you can see like the error is in nanometer range. So this is the point which I want to tell you, that in microprinting we are going to develop the entire system to like gearing or turbine or some microturbine or something like that in the micron dimensions, which are ranging from 1 to 1000 micron. And then you require the scanning mechanism which is going to give the accuracy or the resolution in the range of the nanometer, then only it is possible. So these results demonstrate, this actual results demonstrate that the mechanism is capable enough to develop the scanning resolution in nanometer, and thus it can be set to develop fabrication of the component. So far we have seen the design aspects of this MSL system. Now we are into the fabrication of the component. So uh, during the fabrication of the component, we have employed the focusing lens from the Newport, and Newport this lens optical systems gives their focusing distance. So around that focusing distance, the line is scanned, and for the line scan data, the we have from the optical microscope obtain the width of this line to determine the exact focus. So Newport gives the focus from their data sheet, but there may be some kind of the error in the application when we are putting the lens into the system. So we have to reconfirm the whatever the best focus point. So for that, this laser is scanned onto the photopolymer, and then after for each of the scan, then the distance of this width of this line is measured, and wherever we get a good minimum distance of or the width of this line, that is the actually the perfect focus distance. So that is done using this experiment of the curing by line way, and then the focus is determined in that way, and that focus is point out to be like 8.55 in this case of the developed MSL system in our laboratory. And then the Suhas has done a lot of experiment, typically in the before the fabrication of the 3D components into using this system. So he has characterized the system from the error point of view. What he has done, he has developed a CAD model of circles, okay, which are ranging from 500 micron to the 50 micron. So the C7 is a 50 micron circle, and C1 is a 500 micron circle. And you can see the different circles ranging in this particular dimension, like 400 micron, 300 micron, 200, and so up to the 50 micron circle, that is C7. This is the CAD model, and he has run this. He has fabricated this geometry in using this system 4 times. So 4 times he has fabricated, and then this is one of the result of the fabricated structure. So this is a CAD model, and this is a fabricated structure out of it. And these are then measured using an optical microscope, and then the average of four is taken and recorded. And based on this average and the model dimension, the error is estimated. And then this error is calculated in percentage way. You can see for the first circle of 500, the average dimension obtained is 506.665. Error is 6.665 micron, and the percentage error is nothing but 1.33. So this way the percentage error is calculated for all the circles, and it is obtained as 18.45. Now for the circle of minimum dimension like 50 micron. Now very important point here to tell is that this is the case of like the circles being hollow. So these are all hollow circles, and this outer part is cured, outer part is solidified. Okay, and the circles are nothing but the hollow. So when the circles are hollow, then the obtained dimensions are bigger than the model dimensions. So this is why this is happening. This is because of the shrinkage during the photopolymerization. So you have to consider this photopolymerization or physics of the photopolymerization as well for accurately fabricating the 3D geometry. Now, the next slide depicts the same kind of a dimensions of the circle, but these are solid circles, and outer geometry, outer part is nothing but the uncured part. So these are the cured circles are cured. The circles are solid. And the same for the same dimensions, again the 4 times readings are taken, 4 times they are fabricated, average is taken, and then the error is recorded. We can see now the circles which are fabricated or the solid are lesser than the actual dimensions in most of the cases. And the error percentage error is again recorded. Maximum percentage error recorded is minus 7.19 for the low or least diameter circle. So the care has to be taken about this shrinkage allowance in modeling the CAD model. I mean, in CAD model, typically when the features are of lesser size, this shrinkage allowance need to be given. Okay, and the shrinkage allowance is depending upon the part of a geometry, its orientation, and also the size. You can see the size is more, the percentage error is less. Size is less, percentage error is more. So shrinkage is more prominent when the size is less. And also the shrinkage also depends upon like what kind of the orientation, either it is a cured one or it is a solid one. Okay, so that also is very, very important. Similar dimensions are taken now, 500 by 500 and 50 by 50, but for the square geometries, instead of a circle, now the geometries are square and they are fabricated. And then similarly, the error is recorded and the percentage error is recorded. You can see like the different figures has uh, come up again for the geometry when it is a change from circle to square. And then these are the solid square. Now this were the hollow one and this is the solid one. And again, the different distortion figures has come over here. So this is very important. This a point to understand is that this distortion, this photopolymerization is also playing a very important role, and this physics need to be considered while modeling the 3D CAD model. So whatever the final output you want to fabricate need not your CAD model need not to be of the same dimension, because this photopolymerization shrinkage you have to consider, and that allowance need to be given in the CAD model. Then only you will be able to fabricate the structure of desired size. So based after all this characterization about the system, about the photopolymer capturing the photopolymerization process and all, then the 3D structures are developed. So these two structures are developed by the SOAS in his time, and these two structures are developed by me during start of my PhD program. So you can see like here, the first structure is a cone type of structure. Okay, these are the cones formed by layer way. You can see the staircasing effect on the lateral surface of the component. Okay, these are the four cones. The base diameter of the cone is 448 micron obtained in ACM through the ACM image. The target dimension is 450 micron. Obtained is 448 micron. Height of the cone is the 423 micron, whereas the height in the CAD model was 425 micron. The second picture is the micro pyramid. So again, you can see the staircasing effect. Okay, staircasing effect. So to minimize the staircasing effect, as I told you, you have to uh, slice this 3 component in more number of way, but that will lead to a higher production time. So this is a micro pyramid, and base of this micro pyramid, this base is 996 micron octane. The in a CAD model it was 1000 micron. Top land of the pyramid is 274 micron. Top land of the pyramid is in CAD model it was 275 micron. Then this is developed for one of the application, this micro channel fabricated of 4 mm by 4 mm. But you can see the feature size here, the channel dimension. These channel dimensions are of 146 micron, and there are the counter holes which are of dimension 740 microns and 417 micron. So there are two holes here. The bigger hole is of 740 micron, and the smaller hole is of 417 micron. So this figure, this demonstrate this fabrication of this particular structure demonstrate that the MSL is capable of fabricating large range structure, but a high resolution. When the resolution or the channel dimensions are in microns, but the range is in mm. Okay, so it is capable to fabricate such a large range, high resolution structure. So this is what it is actually it is demonstrating through this particular structure. Otherwise, using mirror scanning, mirror tilting, this is not possible. because when you are tilting the mirror, the your focus spot do not remain constant and it get defocused. The spot size becomes too large, and that's why the resolution is lost. Okay, but with on-axis scanning scheme, it is possible to fabricate large range, high resolution structure. Last structure here at the bottom is showing the large tank and tank in tank, or large range in micro tanks. I mean, so this is a bigger tank here, which is of 4 mm, and the this is the inside the smaller tank, innermost tank, which is of 696 micron by 697 micron, means 700 by 700 micron actually. Uh, in CAD model, and often dimensions are 696 micron by 697 micron. So this demonstrates that this MSL can develop the structure of large range and high aspect ratio. You can see large range 4 mm by 4 mm, and high aspect ratio, that innermost tank is of highest height. So that depicts that we can fabricate the high aspect ratio structure as well using this particular process. Now, this is all about like features of the process. What are the limitations? So limitation is that the using MSL, there are the staircasing effect in the build direction, and that is inevitable. So you can see like in first two structure, the build direction, there are the layer by layer it is formed, and the staircasing effect is like clearly seen. And this multiple layer, if you have to avoid this, then you have to slice in more, and if the slicing more, your development time will be more. So multiple layer will lead to longer build time. Okay, so these are the limitations of the MSL process. And with this limitation, uh, this leads to the new approach uh, to the fabrication, that how to minimize the staircasing effect. So there are various methods which are uh, which are developed, which are given by the various researcher here. So this one is the parameter estimation method, which is given by the David ETL. So what he does is, when he is scanning at the end, when it is scanning at the end, he extends the scanning and change the laser parameters such as exposure intensity or the laser scanning speed and so and so. So with that, the exposure energy is control, I mean to say, and with that exposure energy control, this smooth surface can be achieved. So this is one method. Another is the adaptive slicing. So wherever there is a curved surface, you have to slice in the more number of ways, and I mean more slicing is to be done. And wherever you require there are the straight surfaces, you can have the force slicing. So this is nothing but the adaptive slicing, which is developed by the Pandey ETL and Cormier ETL, and so on, so other by the other researcher as well. So this is adaptive slicing. And then next is about the meniscus equilibrium approach, which is given by the Pan ETL. So what he has developed or presented in his approach is that, let us say this is a structure which is to be fabricated, and this structure is he's having the curved surfaces all around here, and then these are the two layers of the structure which are fabricated by layer fabrication. Now what is done is to fill this lateral surface, this structure is taken out. When it is taken out of the resin, there is a meniscus which is formed because of the fluid property. And this meniscus is formed because of the fluid property. And this meniscus you have to form in such a way that the meniscus surface is conforming to the actual geometry of the surface which is desired. So you have to have this layer thickness in such a way that the layer thickness and the orientation of the layer as well, in such a way that this meniscus which is formed, which conforms to the actual desired surface geometry. And when it is done with that, it is taken out of the resin, and then again it is exposed to the your light through this DMD or other LCD, whatever the projection system you are having, and you can cure this uncured resin, which is in the form of meniscus, and thus it will conform to the actual geometry. So these are some of the methods to minimize the staircasing effect. One of the courses also developed to minimize the staircasing effect is nothing but the single energy exposure lithography. So what is done in single3D process for this 3D micro
Hi, sir. I'm audible.
Hello.
Hello.
Yes.
There is a disturbance from. Means we did not hear you properly. There is some vibration sound.
Is it okay now?
No, sir, not okay.
Uh, okay. So you are not able to hear me.
No, sir. We are not able to hear you properly.
Let me check my uh, I will Hello, are you able to hear me now clearly?
Yes,
Yes,
sir.
sir. Your
Hello,
voice is very faint.
hello.
Yes, sir, now it's okay.
Are you able to hear me now?
Yes, sir. Now it
Yes,
is
sir. Yes,
clear.
sir.
Okay, fine. I have changed
Sir,
my headphones. Sorry for the disturbance. Uh, this bulk lithography is what now I am going to discuss with you. Uh, so in this bulk lithography has, been developed based on the outcome which we have seen from the MSL. That in MSL there are the staircasing effect and all, and it's taking large time for fabrication and manufacturing. So first of all, the central theme. So the central theme consists of like you have the CAD model. So the similar CAD model we have seen in case of the in case of the MSL system, and now same CAD model is taken here in bulk lithography. Now it is sliced here. Now you can see for the each slicing we have got this slice layers. Okay, for each slice plane we have got these slice layers. Now the slicing direction, I mean same component is taken, but the slicing is done in different way. We have sliced in X and Z direction in bulk lithography, right? So this is the X and Z direction in which the slicing are obtained. Now, these particular slices are fabricated in bulk lithography here and mentioned over here. So we are having argon ion for that, then acoustic optical modulator, then the mirror which are mounted on the XY scanner, then the focusing lens, and then through the focusing lens, the focus point is focused at the interface between the transparent substrate and the liquid resin. So this is the difference point. I will take you to the MSL system over here again. So in MSL system, this is what actually has the thing. This is the CAD model slice in this particular way. We have got the circles, and then laser beam is focused on the free liquid surface, and each of this 2D layer is formed by scanning the laser beam line by line way. What is in bulk lithography? Bulk lithography is something different. In bulk lithography, we are having laser light, acoustic optical modulator, mirrors, focusing lens, same, but then there is no free surface liquid, free surface level here. Rather, we are having a transparent substrate, and transparent substrate is kept above the top of the free liquid resin. Okay, top of the liquid resin, I mean. And the focus spot is focused at the interface between the transparent substrate and the liquid at the interface. And now when we are slicing it in this particular way, this first slice is formed by scanning in X direction, and while scanning in X direction, energy is varied. So when energy is varied, the cure depth varies and the first slice is getting developed. So in one line scan, the entire 2D structure is developed here. Whereas in case of MSL, in one line scan, we are getting only line, and by one 2D scan we are getting only one 2D surface, and by number of 2D scans we are getting the 3D surface. Whereas here in one 2D scan we are getting entire 3D surface developed. Okay, so this is how is what is happening in case of a bulk lithography. Okay, so the entire 3D surface is 3D structure is obtained by one 2D scan, and that's why this particular process is called as a bulk lithography. Now there is a very important point here. So how we can vary the cured width here? So cured width can be varied by varying the energy. Now we have done the experiment in a laboratory and we have varied the energy and obtained the cure depth. It is seen that the depth do not increase like by just by varying the energy after certain time, after certain exposure level. Rather it saturates, okay, after certain level. So we are going to fabricate, we can fabricate the structure of certain height only using this bulk lithography. Whereas in MSL it is a keep on building the layer one by layer, one layer by layer, so we can the height is not a limit in case of MSL, but in bulk lithography the height is definitely one kind of a limiting parameter here. So what is the strategy? The on-axis strategy here used. So we are having the mirrors M1 and M2 and focusing lens. The M1 moves along with the lens, but while moving, the energy exposure is varied, and because of that, we are going to get the varying depth structure. How this particular varying depth structure can, or how this energy exposure can be varied? So it can be varied by varying the scan velocity with a constant power. So this is one strategy, first strategy. So you can vary the scan velocity and power is constant, or the intensity of the laser is constant. So with this, what is happening point is, the problem is it introduces the acceleration with varying inertia load, and it requires non-linear control strategy and higher control bandwidth. So that's why this is not practicable. Another strategy for varying the energy exposure is by varying the power with constant velocity of scan. So the velocity of the power can be varied with the velocity of the scan being constant. So the velocity of scan being constant, we are velocity of scan being constant, we are not going to have the problem of the acceleration or the inertial load. And the varying power can be easily obtained by controlling the power using acoustic optical modulator, which is very easy to implement. So the second strategy is varying the power with constant velocity of a scan is quite possible using in the bulk lithography. So this is the on-axis scheme which is used here. So this is the setup, which is improvised setup for the bulk lithography. So again we have the argon ion laser, then the acoustic optical modulator, then we have the mirrors here, then through the mirrors this laser light is passed through the pinhole onto the mirrors of the mirrors which are mounted on the flexural mechanism, and through the flexural mechanism the light is focused at the interface between the transparent substrate and the resin. Okay, and this is the acoustic optical modulator, which is playing a very vital role. As I said, it is not performing only the function of on and off as in case of MSL, but it is performing the function of varying the energy exposure while scanning. Because while scanning, we have to vary the energy exposure to fabricate the device. So this acoustic optical modulator varies the energy exposure while in scanning. So this is the added function for the acoustic optical modulator to perform in the bulk lithography process. Further, when we are focusing the laser light through the focusing lens through this transparent substrate at the interface between the transparent substrate and the resin, there is a change in the path of the laser light, and because of that change in the path of a laser light, the focusing distance do change. Okay, because it is passing through the different materials. So we have to apply the Snell's law accordingly according to the refractive index of this particular material, and then we have to reset the focusing point. So these are some of the points to be considered while doing this or implementing this bulk lithography. So experiments are conducted using this particular the varying energy exposure, the energy power is varied and the exposure time is varied, and with this the energy exposure is varied, and then this exposure is varied on to the different photopolymer resin, such as under the consideration two photopolymer resins are considered here. One is hexane dial diacrylate, that is HDDA, and another is a TMPTA, trimethylpropylene triacrylate, in which the 4% photoinitiator benzoyl ethyl ether is mixed, and this particular resin is exposed to this particular energy exposure by varying the intensity and the exposure duration. And what is measured is nothing but the cure depth and the cure width. And this particular the voxel which are formed by energy exposure are then taken out. We get the meniscus form that has to be removed, and that are removed by the kind of like the process which we have developed, which is simple in nature. We take the tissue paper, we soak this particular uncured resin, and then we put it this particular glass plate on some kind of a wedge and put on some acetone or IPA solution, and because of that we get this voxel structure, clear voxel structure, and then they are ready for the characterization under the optical microscope. So we have observed this voxels under the optical microscope, and then the different cure depths are obtained, and you can see this particular structure here. This is the area of the micro voxels which are obtained here, and this area of the micro voxels are again the characterized through the scanning electron microscope along with the optical microscope image here. Now, what is the basic thing here in case of a bulk lithography? A lot of like the uh, physics, multi-physics is involved in this particular process. You have the Gaussian intensity beam of a laser, and the laser beam is the focus at the interface, and then the photopolymer resin absorbs the photons, and because of that absorption, the Beer-Lambert's law is applicable there, and according to the Beer-Lambert's law, we get this energy at the different location in the photopolymer resin. Okay, and working with this Gaussian distribution and the Beer-Lambert's law, we get the Beer-Lambert's cure depth model, which is given as CD is equal to dp log of Emax over EC. The CD divided by dp is a dimensionless cure depth, and log of Emax over EC, this is the dimensionless energy. So this particular Beer-Lambert's law is plotted for by the different researcher, and it is seen that typically up to certain energy exposure, this Beer-Lambert's law is applicable. You can see like Beer-Lambert's law line here on CD over dp against the log of Emax over EC graph is a straight line of 45 degree, and with all other like photopolymers taken here such as UV101, SCR200, SDD, and so at energy exposure of 0.1 second, it obeys this Beer-Lambert's law. But as we conducted experiment beyond certain the energy band, we have seen interesting result that beyond some critical, beyond some energy level, the cure depth is not increasing, and not, I mean, Beer-Lambert's law is not followed. Rather, we get a slow transition from the Beer-Lambert's law, and we get the saturation regime afterwards. So these are the three regimes. So one first regime is where we get the Beer-Lambert's law applicable, transition from the Beer-Lambert's law, and then the saturation. So these are the three distinct regimes which are obtained when we expose the photopolymer resin beyond certain energy band. Then all these results are taken at the different time interval for the different time of exposure are plotted on against the time, like let us say for shown here in the figure like 0.3 seconds, 0.6 seconds, 1.3 seconds, and 2 seconds. The interesting result we obtain here that for the constant energy exposure, even for a constant energy exposure, the cure depth is the different. Okay, so for point A, the point A is obtained on 0.3 seconds energy exposure curve, and D is obtained at the 2 seconds energy exposure curve, and the cure depth obtained at the 2 seconds is different than at the 0.3 seconds. The reason behind this is that when the exposure duration is large, then the photopolymer photoinitiator species do get sufficient time to come to the reaction zone,
and then absorb the photopolymer photons over there and do not allow the light to penetrate to a large distance. So at the large exposure duration, the cure depth is less, whereas as lesser exposure duration, the photoinitiator species do not get a sufficient time to reach to the photopolymer reaction zone, and thus the light is going in a vertical direction, and thus we get the more and more pure depth in that case. So this is the physics involved over there. This characteristic is then captured with the help of the empirical relation. I will skip this. Someone interested can contact me later on for this particular matter. Then similar to the cure depth, the cure width, and the cure width is also the normalized and then obtained. And this particular characteristics is obtained. This is typically to have the good surface roughness of the final product. Okay, this characteristic is helpful for that particular purpose. Then the surface roughness is also characterized with respect to the energy exposure, and we have got again the three distinct regions. Regime 1 where roughness increases sharply, regime 2 saturates, and regime 2 tends to saturate, and regime 3 is the saturation regime. And this is the typical the surface roughness obtained at the different regime illustrated here. We can see in the regime A, regime B, and regime 3 the different surface roughness are obtained. The regime A is for line spacing which is greater than the line width, and the number 2 B number B is for line spacing which is equal to the line width, and number C is line spacing which is less than the line width. So when line spacing is less than the line width, what happens is light is passing through the already cured resin, and there is a light scattering effect, and that's why the surface roughness is not good. Surface roughness is not obtained. When the line spacing is greater than the line width, then it is obviously there will be a gap between the two lines scan, and that's